Hello, everyone. This is going to be a quick review of Lab 11. Now, I have made some adjustments both to the code and to the analysis in general. So if you have viewed this lab in a previous version, perhaps it is a good idea to review it now. Also, apologies for the tardiness. I am completely overwhelmed. I'm hoping to catch up soon, but so far the whole shenanigans with Zoom is taking up so much time. So anyway, we'll have to kind of plow through it. In this lab, we're going to talk about one-way ANOVA. We have discussed this already in class. We're almost done with it. Let's see now the corresponding codes. The first thing I want to do is I want to introduce a couple of libraries besides the easy packages, which we always use. We're going to be using the LSR, PsycCar, Agricola, Tidyverse, Knitter, Cable Extra, eMeans, and Multicomp, all of which are going to be very useful to do both the ANOVA and the post-ANOVA analysis, and also the Levene test at the very end. So make sure that you have all of them installed. If you look at the notes up here, there's this very, very useful function, the IPAC, that will take all these packages, check if they're already installed, and if they're not, install it for you. So please run this function prior to running anything, just to make sure that you have all the packages, or you can go ahead and install them one by one. Now, the first data set that I'm going to be using is called diets, and this contains some numerical values, about 3 diets. I got this data set through some consulting that I had in the past. And you can load it in by using the read.csv. Again, make sure that the document is at the same spot, set session, set working directory, the same file location, make sure that the code that you're working with is in the same directory. And if we read this one in, as I said, it has 75 observations. As you can see here, you have 75 people, their gender, their age, height, and the weight prior to the diet and the weight after the diet. And we have 3 data types, 1, 2, 3. So what I'm going to try to do first is I'm going to create a new column, which is going to be the differences pre the diet and post the diet. So you can do that easily with the function mutate that comes from the package Tidyverse. So let's go ahead and now start with a data set diets and mutate, create a new column, which I'm going to call weight diff as the difference between these two. So if I go ahead and do that, you will notice now that I have a last column at the end called weight diff, and it's literally the difference between this column minus that column. All right, now what I want to do with it is I want to basically try some sort of analysis of variance for that column by the 3 diets, right? Before we even do that, let's do some simple summary statistics. Let's start with a little side-by-side box plot, which, by the way, is very, very essential when you're doing ANOVA, especially with more than a couple of groups. As you can see here, I'm using again ggplot. The data set that I'm using is diets, and on the first, let's do all the diets together just to get a feeling of how the weight difference is distributed. All right, and as you can see, the plot's one. Here's the plot for all the diets together. All right, this gives us an idea of where the change in the weight was for all diets combined. Now, if you want to do something a little bit more elaborate, and of course, you can use, the corresponding functions to save it, the ggsave, right? So let's go ahead and save this one as weight difference PDF. This is all of them combined, right? You just need to give it a name and then the same plot 1 that we saved here. We have used ggplot in the past. They should be straightforward. Now, what I want to do is I want to do some summary statistics, as I mentioned, and you can do the summary statistics for all of them, but let's try and do summary statistics by diet types. And we're going to be using the function describe by. You just need to provide which variable you're analyzing by what group. And when I run it, you will see this classic table here. This gives you the mean, median, standard deviation. One thing that I want you to note is that all groups have the same number of observations. So we're talking about balanced ANOVA. Okay, now let's continue on and do some summary statistics. So let's do some specific summary statistics. I've shown you this code in the past. Describe by has a lot of things that it's popping up, just by default. If you want to customize everything, there is really quick thing that you can do with the function summarize from Tidyverse, and this way you can just choose whatever you want to show over there and drop the rest. So there you go. The upshot of this also is that you get a very nice clean data frame that you can then save as a CSV. Anyway, any way that you want to do it, it's fine by me. All right, let's proceed and continue on with a little bit of a graph. This is the important graph, and I want to see this in any sort of computations where an ANOVA is involved. This is the box plot by diets. Note here the syntax. You need to give it the data set. You need to tell it what variable you're analyzing, weight diff, and by what variable diet. Then, if you'd like, you can put the error bars. You can put a little title. One thing that you should note is the labels can be adjusted as well. The title can be adjusted. Everything basically can be adjusted with the ggplot. Whereas with the plot that R comes by default, things are a little bit trickier. This does look like a longer code, but it gives you a lot of options. So let me go ahead and run this. And as you can see, this is the side-by-side box plot that also has, as you can see here, the averages for each of them. This is the start summary function equals mean. If you want to save this, you can use the codes beneath with another GG save. Let's go ahead and do that. And I'm going to save the PDF for now, but you could save the JPEG and other formats. So let me go ahead and save it. There you go. And now it is saved. Again, it gets saved at the same folder as you can see here. All right, let's continue on and try to now actually do some, diagnostics. Let's try to figure out if the variables that we're looking at, if the variable that we're looking at by these groups is normally distributed. One way to do that is utilizing the QQ-plot just to get a feeling again. We will later on see some sort of actual statistics for it. This is literally like some diagnostics. It is a good idea to put it there. So what this is going to do is it's going to create QQ-plots for the variable weight diff by the different diets, and the facet wrap down here. I should put a plot 3 so we can see it. The facet wrap is going to put them right next to each other. So as you can see, we have 3 plots. These are the QQ plots for the first diet, second diet, third diet, right? And again, we're saving it as a PDF at the end. Always a good idea to put these things there. It's just a little diagnostic. It helps the reader understand how your data looks like. And if you also want to create some histograms, side-by-side histograms, you can use this command. And as you can see, again, we're using the dataset diets, we're using the variable weight difference, and we're filling it by the different diets. You'll see that just changed the coloring. You can play around here with the breaks. Remember, these are like the bin sizes if you'd like, and also like how long or how small you want this to be, right? With the X lim and the Y lim. If I run this, and I should again put some sort of plot 4 here so that this pops up. If I run it, you will see down there. There it is. Here are the box plots. Basically histograms, I'm sorry, for the 3 different diets. Again, a good diagnostic. It is a good idea to kind of like see how these things are distributed and have it on the side. All right, let's now dive into the actual ANOVA. And remember, in an ANOVA analysis, the null hypothesis is that the average of the 3 groups is the same, and the alternative is at least one of them is different than the other 3. The line to compute the ANOVA, as you can see here, is very straightforward. It's literally like this little piece. I'm going to create the ANOVA with the function A of V. You need to tell it what variable to analyze by what grouping, and then give it also the data set. I'm saving this as diet.AOV because I'm going to be doing a lot of things with that at the end. But if you run these 2, you will get the classic table that we know down here, right? And if you focus on the p-value over there, we note that this is smaller than 0.05. Therefore, at least one of the groups is different than the rest, okay? So the ANOVA tells us that, yeah, there's probably some sort of difference. Remember that how we compute that F value here, right? It's the ratio of this guy divided by that guy. And so right now we can say, yes, at least one group is different, or 2 groups are different, or all groups are different. In order for us to actually dive into it, we have to do what is called a post hoc ANOVA test. And I'm going to start with Tukey. We also looked at LSD. We looked at Bonferroni. All of them are available. I promise you, for whichever post hoc you want to do the analysis for, there is a certain code in R. But what I'm going to do first, before I even do that, I'll show you what would happen if we forgot that this is an ANOVA and just straight up tried to do pairwise t-test comparisons amongst the different groups. There's a shortcut for it. It's this little command, the pairwise t-test. In order for that to work, though, you need to put this little with diets and whatnot. It's a little bit of a strange format. I don't really like it, but it's going to do what we want fast. So as you can see, this is going to do pairwise comparisons of the variable weight difference by all possible combinations coming from the group diet. And it's not going to be adjusting them. So these are literally t-test, and as a matter of fact, it just does pool t-test. I mean, it's not a big deal, but what I want you to focus on here is that, look, it gives it to you as a comparison table. So group 1 with group 2 have a p-value of 0.9, group 2 with group 3 have a value of 0.0091, and group 1 with group 3 have a value of 0.00122. So if we use this to do the comparisons, we would say, for example, that group 1 is statistically different than group 3 because the p-value is smaller than 0.05. And group 2 is statistically different from group 3 because, again, they're the same reason. But groups 1 and 2, we don't have enough evidence to suggest that they're different. Okay. But remember, this is if we don't make any adjustments. We're doing straight up t-tests, and that's not the right thing to do, right? So instead, what we can do is we can do the pairwise t-test, but with some sort of adjustment. Okay. Let's do first the Tukey HSD, and the Tukey HSD, Tukey honest square difference, takes in the whole model that we computed here, the diet.AOV, and some confidence level, right? For 5% rejection region, you just put here confidence level 0.95. So when you run it, you get this kind of table, and at the very end, you're getting the adjusted p-values between these specific groups, right? So once again, if I'm looking between group 2 and group 1, they don't seem to be statistically different. Groups 3 and 1 are, but now note that the p-value here has increased. So this is close to 0.03 when it used to be, I want to say, yeah, 0.01. All right. So, and that's the idea. When we do these adjusted pairwise comparisons, it is always the case that the p-value is a little bit larger, making rejecting the null hypothesis harder. But this is the honest way of doing it, okay? And similarly, again, groups 3 and 2 are statistically different. Again, your p-value is smaller than 0.05. Now, what I want to say is that this is the table that we should be looking at, right? Not the unadjusted one. But even with this table, we can see that indeed groups 1 and 2 look similar, and they're both different than group 3. All right, so let's continue on. If you want to create now some sort of comparison of the differences in a confidence interval way, so like report the difference and confidence intervals amongst all groups, the commands that you need to do, and I'm not sure why this got spread apart, but let's see, let's put all of them together. The command that you need is this guy. It's going to create some comparisons amongst all groups. Let's see, and I also need this one. Okay, so you need all 4 of them to do the nice plot. And what this is going to do for us when I run it, it's going to create, as you can see here, it's going to create the differences between every possible group. So between 2 and 1, 3 and 1, and 3 and 2. And it's going to put here the 0, right? So remember, if a confidence interval hugs 0, it means that probably these two are similar. Of course, you need to do the pairwise comparison with an actual t-test, but this is like showing us here that groups 2 and 1, their difference is hugging 0, so maybe they're practically the same. Whereas the 3 and 1 and 3 and 2, you see the confidence interval does not hug 0, and even when we did the pairwise comparison with the Tukey, we saw that they are statistically different, right? So this is what this one does. All right, very good. And let's move ahead. Besides the Tukey test that we mentioned here, we have the Bonferroni adjustment. As I said, Tukey is more powerful than the Bonferroni, but just in case you want to do it in general, this is how you do it. And this is more general than just ANOVA. It will work with any sort of pairwise comparisons. And again, I'm using the pairwise function. I know it's a little bit clunky, but this is the fastest way to do it. You present it with the variable that you're trying to analyze, the grouping, and then the adjusted method here, you just type Bonferroni. So what this is going to do is, again, in a triangular way, it's going to compare group 1 with group 2 with the rest, and so on. Note again that the p-values between 1 and 3 are smaller than 0.05, and between 2 and 3 are smaller than 0.05. But once again, these p-values are larger than the unadjusted one. So both Tukey and Bonferroni make rejecting the null hypothesis harder by pushing the values a little bit higher up. In the lecture, we said that the Bonferroni works with dividing the alpha level by the number of comparisons, but this is completely equivalent to multiplying the p-value with the number of comparisons and compare it to the initial alpha level. And that's how this one is worked. But these two concepts are completely equivalent. All right. So now that we analyzed the Bonferroni as well, let's jump back and look at the least square difference. And I remind you that the least square difference is, you compute the standard error and the degrees of freedom for all pairwise comparisons, and then just find the difference between the two, right? And then check it to see if they are the same or different. Now, with the least square difference, you could also look at groupings, right? And remember, the groupings, the code for that is this. It's going to try to find the differences, and then if two groups are statistically the same, it's going to give it the same letter. If they're statistically different, they're going to get a different letter, right? So with this situation, we're computing the least square difference, and if you just do K and then $ groups, you see the different groupings, right? And now we see that diet 3 is on its own group, and diets 1 and 2 are a group themselves, right? So if they share the same letter, they're in the same group. If they don't share a letter, they're in a different group, right? So either or, least square difference, Tukey, some sort of post-ANOVA test is needed. You cannot just use pairwise differences. That's what I want you to use here. And again, it depends on either the bibliography or your personal preference. All right, now, so far I've been working with a balanced design. You saw that all groups had 25 observations. Let's see what happens when we're doing a one-way ANOVA with an unbalanced design. Nothing really changes, but you have to be a little bit more careful on how you interpret the results, especially if it's truly unbalanced. What I'm going to be using now is the dataset tomato. And let's put a little break here so that we know what wait a second. So in this data set, we have various values for different strands of tomato, basically different genotypes. And the one that I'm going to be looking at is the length. This is the length of the roots. And we have, other values here that we could potentially analyze. Note that while I was reading it with the read.csv, I made sure that the genotype, the variable genotype, was read as a factor, right? So in a lot of these types of analysis, you may run into trouble if you haven't set your variables right. If you want to do a multi-way ANOVA, make sure that all your input variables, your classes basically, are turned into factors. And when you read the CSV, this is the best time to do it. Just like this, you do call classes, and then you just put a list here of all the values that you want and what type of variable they are, right? Okay, so now if I look at the analysis that I want to do is, again, a simple ANOVA, but once again, let's try to do the basics, some sort of graphs. Let's do the box plot by all three genotypes. Again, I'm not going to worry about how it looks like with all of them combined, but I do want to figure out how it looks with different groups. And as you can see, this is comparing the root length for the various genotypes, and we have line A, line B, and the M82. All right. These box plots are really good to have. It's very informative. Put them in your presentation, put them in your graphs and all that. Now let's move on and look at, again, let's try to save this. It is always a good idea to save it as a PDF so that other people can see it. And let's move ahead and do some sort of descriptive statistics. And I've used many different ways to do descriptive statistics. Here's another one with the describe by, but in this case, I'm going to change it into a little table, and I'm going to select the ones that I want and even change their names. Okay, so many ways to do summary statistics and keep what you need. The upshot again for this is that it's now saved as a data frame, and you can basically save it in R or SAS, right? sorry, you can save it as a Word document or as an Excel document and give it to somebody else. All right, now, after we do the summary statistics, let's also try side-by-side box plot, side-by-side histogram. Again, the technique is the same. I'm gonna do the data frame tomato. I'm interested in the length by different genotypes, and I'm wrapping them by genotype. You'll see that just puts them next to each other. As you can see here, this is it. Now I may have chosen the breaks a little bit better. Here I'm choosing them from 200 to 800 by jumps of 50. Completely up to you how you're going to do it here. All right, now let's go ahead and do the actual analysis after we save it. Canvas block 4. Let's save this one as well as a PDF or JPEG, whatever you need. And let's see. Here's again the one-line way of doing ANOVA with the summary statistics directly below it so that we can get the table. And again, you need to tell it what variable you're analyzing, by what grouping, in what data set, and summary at the end. And there we go. Now their p-value is 0.642, which implies that we failed to reject the null hypothesis, right? Our p-value is much larger than 0.05. So technically we could stop here, right? There doesn't seem to be any statistical difference between them, or at least we don't have enough evidence to suggest that there's a difference between the averages of the 3 strands. But if we wanted to do that anyway and try to do, for example, some sort of like pairwise comparisons, we can use this post hoc pairwise test, okay, which is an equivalent way to analyze the post ANOVA test. And if you put method equals none, this just straight up does pairwise t-tests. If you look at that, all p-values of the pairwise comparisons are larger than 0.05. So indeed, even in this case, we failed to reject the null hypothesis. It seems like all pairwise comparisons do not give you statistical differences. If you want to now look at it as a 2-key, again, I'm going to be using the tomato AOV. Same deal as before, and again you will see like the p adjusted, all of them are much larger than 0.05, and they're also much larger than these, right, that we've discussed. That the 2-key always pushes the p-value up, making rejecting the null hypothesis harder. So again, no statistical differences here. And if you want to do it with the groupings, there we go. Again, the groups are the same because they all get the same letter, right? So in this case, yes, there doesn't seem to be any difference. If I want to now check my assumptions, and here's where the interesting stuff happens, and you should have done that for the previous one as well. I just decided to do for one of the two. And you should check the assumptions. The first thing that you need to do is, we said, you need to basically check the residuals. There is a standard way of doing it. First, you need to plot the residuals utilizing this command. And again, I'm not sure why it was split. Oh, no, this one is not split. It's fine. So if you do this, these are called the diagnostics for the residuals. And one of them here is the QQ plot. We'll get back to that a little bit more. But you also have the residual versus fitted, the residuals versus the leverage. We will come back to those when we do the linear regression. But for now, you need to report this table as well. This is gearing towards like checking that the residuals are normally distributed. And you can do that basically by isolating those residuals. As I said, this tomato AOV has a lot of things in it. So if you just extract it with this command, residuals object equals tomato AOV, and name it something, I'm just going to name it tomato.ANOVA residuals. Then you can do things like, I don't know, like create their histogram, and there are faster ways to do it. But for now, I'm just looking at it, and also check if they're normally distributed. So to check if they're normally distributed, you're using this KS test. You could describe them as well, just to get a feeling, because we need also this feeling to do the Kolmogorov-Smirnov test, which actually I'm thinking about switching to Kolmogorov-Smirnov from the bibliography. I believe this is a much better normality test. So from now on, like if I'm going to use normality, I'm going to do Kolmogorov-Smirnov. It seems to be more powerful than the Shapiro-Wilk. But in order for it to work, at least in this implementation, you will need the mean and the standard deviation of this group. So always do some sort of description and then follow it up with this, right? So when I describe it here, at some point, I need to figure out the mean and the standard deviation, and those are needed, as you can see, when you're running the Kolmogorov-Smirnov test. But that works by providing the variable, utilizing the normal distribution. You can change this to other distribution, but p norm for now, and then report the mean and the standard deviation. All right, so when I run this, this gives me 0.4468, disregard the wording for now, but this is much larger than 0.05. So we can assume that yes, the residuals are, at least they're not normal. They are, we don't have enough evidence to suggest that they're not normally distributed. So we can proceed. Now, what else? The other big thing that we need to do is check the homogeneity of variances, the homoscedasticity, that is, and we discussed that this is done by the Levene test. I found various implementations of the Levene test. This one seems to be the easiest one. And again, you need to provide which data set with tomato, and then the Levene test of what variable by what grouping, and center it around the means. And as you can see here, my p-value is smaller than 0.05. So unfortunately, the variances are not the same. They're statistically different. We report this as a shortcoming and continue on. Now, in the future, you could have taken like larger data sets. You could have tried to, artificially change the variance by trimming it. Or, if everything fails, you could even like switch to a different analysis besides ANOVA. For those of you that are using ANOVA in a project, just report this, and even if it's problematic, continue on using it. All right, so that's more or less what we want to discuss here for the ANOVA. I do owe you a little bit more of an explanation of the residuals, but let's wait until we do the linear regression first. Okay, that's it for today, and I'll see you in the next one.